free training provided by the HVAC School podcast is made possible because of the generous support from our sponsors, Testo, RectorSeal, and Carrier. All right, if you guys have listened to this podcast for any amount of time, you know that I kind of have a little bit of a crush on the Testo 605i. It's just a stupendous, can I say stupendous and not have it seem like hyperbole? I'm going to choose to say stupendous. It is a stupendous tool for the investment that you spend on it. It is a great thermal hygrometer. And for those of you who are like, what the heck is a thermal hygrometer? Well, let me tell you. A thermal hygrometer is basically a digital psychrometer. That's another term for it. And it measures wet bulb, dry bulb, relative humidity. The dew point, it can extract all of those. If you've ever looked at a psych chart, you need a couple pieces of information, and then you can extract the rest. But what the 605i does really well is that you can measure these readings in duct. So you can take wet bulb, dry bulb, relative humidity in the return, wet bulb, dry bulb, relative humidity in the supply, and right there in the SmartProbes app, it will actually calculate delivered capacity as long as you enter the CFMs, which is pretty cool. CFM. I always want to say CFMs, CFM of air. So the 605i is a great tool, but when you add in what Jim Bergman is doing with the MeasureQuick app, which you can find out more by going to measurequick.com/download now on that application. I'm excited about that product. But the Testo SmartProbes and the Testo 605i work with Jim Bergman's MeasureQuick app. And so you can get the best of both worlds, a really, really highly functional app plus the Testo 605i. So the actual SmartProbe app that you can use directly with the 605i, it works great, but you can extend its functionality by using it with the MeasureQuick app. And so getting delivered capacity is a huge thing. I mean, you can actually show your customer right there on your phone. We've already done this on many occasions. Like, look, this is how much capacity this system is actually delivering. Here's what you paid for. Here's what you got. It's a great product. And it's also just a great way to get your indoor wet bulb and dry bulb, which you need anyway if you're going to calculate superheat on a fixed orifice system. If you want to use it to calculate target delta T, air temperature split, it's also great for that. It's just a good all-around temperature measurement device. Plus, it gives you that additional data that you can only get from a thermal hygrometer, and you have the ability to get it in the duct. Plus, it's Bluetooth. And like I've mentioned a million times, you can get that particular product, the Testo 605i, by going to TruTechTools.com. And at checkout, use the offer code GETSCHOOLED, all one word, no caps, no spaces, GETSCHOOLED. Look at the bottom left-hand side of the screen when you're in the process of checking out there, and there's a coupon code box, and you type GETSCHOOLED in there, and you will get a great discount.
Meet Zoomlock, the 10-second flame-free refrigerant fitting from Parker. Reduce labor costs by 60% with no brazing, no flame, and no fire spotter. Discover how Zoomlock can help you be more efficient and productive. Visit Zoomlock.com for more information.
This is the guy who gets excited whenever he learns something new about HVAC, which is every day. Which means he is always a little too excited for a grown man. Brian Orr.
I think winter is officially upon us. It actually doesn't feel cold at all because I live in Florida, and in Florida it never gets cold. We had one night where it got down into the 40s. But today's podcast, oh, by the way, I'm Brian with HVAC School. This is the podcast that helps remind you of things that you might have forgotten about the HVACR trade, or maybe reminds you of some things you forgot to know in the first place. And today's episode is about history of gas furnaces, introduction to the history of gas furnaces, which sounds very intellectual, but the fact is that it's actually very practical. And of course, whenever we have Jim Bergman on, he's going to bring it, and he's going to embarrass me. And this episode is no exception to that rule. So we go through all the way from old gas. We actually start with wood-fired appliances, and Jim takes us all the way up through the modern modulating high-efficiency furnace of today, and just everything in between, and all the safety, and just the different kind of the idea behind why these changes have happened in gas furnaces, and gives you a really good kind of basis. And then in future episodes, we're going to talk about combustion analysis, we're going to talk about the diagnosis and sequence of operation of different types of furnaces, and we're going to talk about the proper commissioning of gas furnaces, all with Jim Bergman over the next several months. But this is a great episode. Hope you enjoy. Here we go. Jim Bergman, the history of gas furnaces. I'm here with Jim Bergman. Jim, it's been almost a month since you've been on the podcast. My numbers have been diving. I was thinking about just closing up shop and just saying forget it if I couldn't get you on. So I had to beg and plead.
It was the best month of my life. I mean, I really can't complain too much. Not having to talk to you it made me feel a lot better about things. So
it was refreshing.
Yeah, I needed a little break.
But then you had the need to have a conversation with somebody in which you could dominate 95% of the conversation. So here we are.
Yeah, I guess my wife's gone this weekend, so I got to talk to you.
Yeah, that's true. I'm sorry. And actually, today is going to be worse than usual because unlike some of the other topics that we've talked about, there's even a greater gap in experience between you and I on this topic than even some of the others. So today we're going to be talking about an introduction to furnaces. And I've probably worked on 1,000 furnaces in my career, but mostly it's been just regular maintenance and stuff. They don't really break that much in Florida because we don't run them very much. Let's start by going through wherever you like to start when you're talking about furnaces, introducing them to somebody who maybe doesn't know that much about furnaces.
I actually like, when I would go through this with students, we talk a little bit about each type of furnace. And when I was teaching a high school program, and I actually learned quite a bit along the way because when you get into this stuff, you don't realize the long history we have of using natural gas for gas heating, which goes probably back into the maybe even the late 1800s, 1930s or so, was probably when it was really in its heyday, 1900 to 1930. And everybody had coal furnaces. And then all of a sudden, natural gas became a little bit more readily available. We switched from burning wood and coal to natural gas. And up here, where we're at, you still run across quite a few homes with coal chutes in the basement where they used to have a small door that somebody could open up and they could dump a big old pile of coal in your basement while you were at work or whatever, and all of the heat was delivered by truck back then. So it was a whole different ball game, but it's an interesting part of our history. It leads into a lot of interesting things with gas furnaces that probably some people here have never even thought about before. Because when we first got into gas furnaces, it was actually about modifying the existing coal furnaces we have and putting a new fuel in. If you don't understand it, it leads to a lot of confusion, especially when you start looking at a gas flame. The first question, Brian, I'm going to ask you, because of your huge knowledge of gas furnaces, working on in a lifetime what I've worked on in a heating season, maybe up here in the north, what color should a gas flame be?
Well, I'm going to go ahead and answer what I've always known to be true, and there's no way you can convince me otherwise, Jim, because I know so much about it, and that would be a nice, pretty blue flame is what we want to see. That's
actually what I would think too, but the gas flame being blue is actually a modern thing, and if you get into some of these older furnaces, and I think it's real important, especially for you guys that work up in the northern climates here and run across the old 20th century and Wise Owl gravity furnaces and things like that, a blue flame will actually be about the worst thing you could have in that furnace. It'll completely rob it of efficiency. And let's talk about why that is, because it's fairly interesting. I think it all goes back to understanding, first of all, how furnace burners and how furnaces worked. I mean, we had basically this big old pot that we would put coal in, and we have a fire going in there, big flame in there, heating up the inside of that pot. And it's real important to understand how the heat transferred in that, because these were like really simple designs. And when we think about heat transfer, we got to always think about heat transfer from the flame to the heat exchanger and then from the heat exchanger to the room. It comes down to, well, how were they transferring heat back then? Well, if you think about this real simple design, we talk about how we transfer heat: conduction, convection, and radiation. And radiation is heat transfer like the sun. Conduction means that we're actually heating it up, heating the metal with a flame directly and conducting to the surface. And then we have convection, which we're moving heat from the flame through a complex heat exchanger design. And as the hot gases scrub the walls of the heat exchanger, it liberates the heat. Well, when you look at an old furnace, they really did not have complex heat exchanger design. You had a fire inside, and it basically went through a single pass or maybe a double pass heat exchanger, then exhausted outside, which would result in, theoretically, all your heat going up to the chimney. Well, the question is, why didn't it? What was the method of heat transfer? And when you look at these old gas furnaces and you look inside, you'll see that a lot of them had a bright orange flame. And that bright orange flame was called carbon luminous flame. And it actually was bright orange just like the sun. In fact, that's a good reason the sun is orange, because it's designed that way to transfer massive amounts of heat energy by what method, Brian?
Radiation, Jim.
Radiation, yeah. So if the sun was blue, it wouldn't transmit any heat at all by radiation. It'd be a very poor conductor of heat to the earth, but it's not. It's orange. And when we look at a gas flame in an old furnace, it has to be the same way, because the primary heat method of transfer was by radiation. And this is a good way to understand this. Have you ever lit an oxyacetylene torch, Brian?
I have. I've done that a time or two in my career.
Some guys only use those turbo torches. I wanted to make sure you weren't completely lame and you actually understood what an oxyacetylene torch was. But when you light the acetylene, what do you feel right away when you light the acetylene first?
Well, the first thing I feel is shame because I'm letting little carbon bunnies go all over the customer's house. But the second thing I feel is heat.
You feel massive amounts of heat, right? And then when you dial in the oxygen, we know for a fact the flame gets hotter, but what do you notice goes away?
You know it's hotter, but you don't feel as much heat coming off of it. You don't feel that radiant heat.
You don't feel any heat anymore. And you go, oh, it's because it's a smaller flame. You don't feel any heat. That would seem to make sense, but actually that smaller flame is much, much hotter. So in fact, it is giving off a tremendous amount more heat now that we've mixed oxygen with the acetylene, but we don't feel it anymore. And that's because the heat now is, the color of the flame has changed, and the heat transfer by radiation has effectively stopped. So when we're looking at an oil furnace or in a gas furnace, like especially fuel oil too, you look inside there, you see the flame is bright orange. And again, that's a carbon luminous flame in an oil furnace. Carbon luminous flame in gas furnaces are required so that they can actually transmit the heat energy from the flame to the heat exchanger surfaces. And if you were to install a retrofit burner into a gas furnace or into an old furnace with a bright blue flame, it would actually almost stop transferring heat altogether. All the heat would go up the chimney and the efficiency would go into the toilet. And that's exactly what we saw a lot when people were putting these gas burners into retrofit equipment. And so the color of a flame is very dependent upon the design of the furnace. And for modern furnaces, now we did some things that are interesting. And I want to express a couple of things here that I think are really important. A carbon luminous flame, if it's burning correctly, all it means is that the carbon molecules are actually burning in the air, just like those dust bunnies you have. That's carbon, that's unburned carbon in that acetylene torch. If we're to burn that carbon, burn that dust bunny, it would glow bright orange, and that's exactly what's happening, but it's all inside the flame. And if we're completely burning all that gas up by radiation, we are going to have a fairly good combustion efficiency. And typically, when we're talking about burning fuel, we want to consume all the fuel that's going through the appliance. And so when we're combustion testing, what's really interesting is if you combustion tested a furnace from 1930 and a furnace from 1980 and a new 97% efficient furnace, in the net efficiency, they would all be about the same. They'd all be around 80% combustion efficiency if you looked at basically how effectively we're burning the gas. What changes with these furnaces when we get into newer furnaces is actually how we utilize the heat that we're producing. So when you look at combustion analyzer, it's actually not analyzing the combustion process when you look at the efficiency number. It's actually a modified equation that takes into account not only the combustion efficiency, but also associated stack losses. So it's a hybrid equation. It's really not truly a combustion efficiency calculator. It's combustion efficiency and stack losses. And stack losses are those that are heat going up the chimney and then also excess air. So when we look at that, a couple of things are important, but it's a little bit of a sidebar. We'll get to the next one on combustion efficiency. But when you look at this, the older furnaces, an orange flame in there is actually desirable, and you can produce an orange flame without producing any carbon monoxide in the flue because, again, if all that carbon is consumed in the carbon luminous flame, then all it's going to come out of the stack is carbon dioxide, water vapor, and heat. So that's why sometimes you look in there, and the reason I think this is such an important part to start with is guys will look inside of a furnace and go, oh, the flame is yellow and it's not burning right. And they'll go and they'll shove the combustion analyzer in a probe and they'll go, how am I not getting any carbon monoxide? This thing's as yellow as could be. And it's actually a yellow, gold, orange color is what is ideal. It's not like a starved flame, which is a little bit different color for yellow, but they're looking at it and they don't know what it is. They assume it's burning poorly and they can assume it's got poor combustion efficiency, but in reality, it's burning safely and it's burning exactly the way it's engineered to burn in that old appliance. The older ones were heat transfer by radiation. Around 1970, right? Because you got to remember too, when you go back and look at this stuff, when we first designed furnaces, think about what we were burning. We were burning wood and we were burning coal, and the flame was in contact with the metal. We had impingement. The outside surfaces would get really hot. So we really needed this really heavy-duty heat exchanger. And a lot of heat exchangers were made out of cast iron. And in fact, furnaces used to take 3 to 4 days sometimes to install because a guy had to pour a pad on the basement floor. He had to haul down cast iron pieces, some of which weighed 200 or 300 pounds a piece. Some of the cast iron pieces weighed upwards of 700 pounds in some of the big old furnaces on there. They had to assemble every one of those pieces. They had to put gasketing in between it, and they had to bolt them all together, and then they had to put fire cement on in between sections. And it was a huge project to put a furnace in your house. I mean, it was a big expense. It was heavy duty. These things would last forever. And we used to say, well, now we look at them and go, they weren't efficient. But they were really quite efficient for their time. And like right now, with cast being so cheap, I think we're at $3 an MCF, you get to the point where you wonder how fast the payback's going to be. That, again, is another discussion, but it's interesting when you look at efficiency in gas furnaces. Back then, it was a big job to put these furnaces in, and big pieces of cast iron. The thing took forever to heat up. Once it got hot, it would tend to stay hot. The old furnaces didn't even have a blower in them. They heated by gravity. Cold air would fall and warmer would rise because it was less dense. So and you had that real heavy cast iron heat exchanger, so it could get up to really high temperatures. Typically around, the limits were set at 225 degrees, 250 degrees. And the thing cranked out pretty warm air and kept your house pretty comfortable. Now, obviously, there's a couple of things that you also got to realize were on this old furnace. First and foremost is the draft hood. When we look at how that furnace exhausted, it's really important to understand what the draft hood is for. And did you ever think about that, Brian? You know what the draft hood is for?
We don't have draft hoods in Florida. That's not something that exists, so tell me more.
Well, you have pool heaters in Florida, right?
Yeah? Okay. All right. You got me. Yeah, we do have pool heaters.
I don't even have to come to Florida to tell you what you don't know. My gosh.
That's true.
All right. All right. So what is the draft hood for on a pool heater?
The draft hood is to actually introduce air into the flue. And actually, I'm not really clear on exactly what goes on. I know it cools the flue gases. At least my understanding is that it regulates the flow through the burner. Am I on the right track here?
No, keep going. This will provide some entertainment for everybody.
I'm not saying another word. I'm editing it all out, so nobody's ever going to hear this.
No, it was really good. It was really good because what you said is what everybody thinks the draft hood is for, and
okay,
that is completely wrong.
Okay.
The function of the draft hood is to separate the appliance from the draft.
Okay.
Why would you want to do that? Well, let's think for just a minute what happens. So in order for air to come into a furnace, in order for combustion air to come in, what has to happen? Now, there's two airs that go in a furnace. Obviously, we'll talk about that for a minute. We got primary air and secondary air. Primary air being the air that goes through the burner, that is induced by the Venturi effect, because we're shooting a stream of gas in there, and the gas entrains air. And in a well-designed Venturi, the proportion of air is proportional to the gas. So as you raise or increase the gas pressure, the amount of air that we pull into the burner also raises or decreases. Now, when we look at secondary air in a furnace, secondary air is the air that goes around the flame and is pulled in around the heat exchanger inlet. So we know that primary air gets into the burner through the gas firing into the orifice. How does secondary air get in?
In most of my modern experience, it's because you have some form of forced induction where it's actually drawing it through with a pressurized inducer fan. At least that's what we call it in Florida. And
we don't have that in a pool heater. In a pool heater, how does secondary air get in?
We have those in some pool heaters as well. But we're going to say a natural draft pool heater, it's drawn in because you're increasing the temperature. So as you increase the temperature, hot air rises and it escapes and it brings air in behind it. It creates a low pressure and high pressure environment that draws air in.
So the heat of the flame is what creates the draft. Basically, it pulls in to the bottom, right? Now, let me ask you a question. Have you ever seen the movie Backdraft?
I haven't.
Going back to the 80s? Oh my gosh, you haven't seen them?
That's when I was born, so...
Yeah, okay. The whole premise behind the Backdraft is that these firefighters, they're fighting these fires, and every time they open up doors, the flames burst out and burn everybody to crisp because the flame is looking for oxygen, right? So when we take a gas furnace and we block the flue pipe and there's a flame in there, if the flame can't get air through the heat rising through the heat exchanger, because now we've blocked that off, if no air can come in, what do you think the flame's trying to do?
It's going to jump back out at you. It's going to roll out.
It's going to roll out, yeah, because it's looking for oxygen and it can't get any air. And hence, that's what the rollout switches were for on modern furnaces. When the gas way becomes completely plugged, The flames come back out the other side. That was engineered to shut the furnace off. Now, back in the day, we didn't have rollout switches on modern furnaces. So what we did is we had a draft diverter, and the draft diverter was designed to disconnect the chimney, the flue, from the furnace. Because if a raccoon crawled down your chimney or something crawled down your chimney and clogged it, well, we would want the flue gases to escape into the basement. You go, oh, flue gases in the basement, this doesn't sound good. But what are byproducts of combustion, of good combustion? What are they? Do you know off the top of your head?
No. Go ahead.
Byproducts of safe combustion are carbon dioxide, water vapor, and heat. That's it. All the carbon in the fuel is converted to carbon dioxide. When we have an intermediate conversion, in other words, like it doesn't all completely convert, we get carbon monoxide. And carbon monoxide is dangerous to humans because basically your blood can't tell the difference between oxygen and carbon monoxide, and you just die from oxygen deprivation. That's what all this is about. When your blood replaces all the O2 with CO, you die a slow, painful death, which probably most people don't want to do. So we try and avoid that. But back in the day, we would exhaust all the flue gases into the basement. In fact, I've run across hundreds of furnaces over my career that are exhausting flue gases into the basement. And you go, well, that's got to be obscenely dangerous. And yeah, it is dangerous because if the furnace were to make carbon monoxide, we'd be exhausting carbon monoxide in the house, which is really bad. But most furnaces back in the day, if they were going to hurt somebody, do you have any idea how they hurt people? It wasn't through carbon monoxide poisoning.
So burning the building down.
It was burning the building down. 100% correct. I'm glad you got one, Brian.
I think this is the second one I've gotten so far. I don't have a great record, but right.
So yeah, burning the building down. Back then, we used to have firefighters, and they had watchtowers, and homes burned down quite a bit because appliances just weren't safe. We used a lot of wood, we used a lot of coal, then we converted to gas. And if we blocked that chimney off and the gas flame was coming out the front looking for air, then it would catch on fire, whatever was next to it in the basement. Again, diverter was put on to protect the consumer from their house burning down. And it was assumed that if we had good combustion, the only thing we'd leak into the basement would be carbon dioxide, water vapor, and heat. And so overall, that's what that draft hood is for. And the other thing is that when we look at the draft hood and we look at the furnace and it's running, it exhausted the exact amount of gas and air that it needed to pull in the amount of air it needed for combustion. In other words, whatever goes in is also what comes out, right? And so the natural draft of the appliance would pull in the exact amount of air that it needed, and it would come out the other side as carbon dioxide, water vapor, and heat. And so the older furnaces, if you measure in before the draft inverter, in other words, you get up inside the cell of the heat exchanger, you'll see that those older furnaces run around 20% excess air. What that means is excess air means that air that was not used in the combustion process. So the furnace is actually supplied with 20% more air than it needs to burn all the fuel that's in there. And excess air is a necessary evil, but it's also a big energy waster when it comes to an appliance. And this is one of the reasons we eliminated the draft hood, because let's talk about this for just a second. For every 1 cubic foot of gas that are burned, you need primary air and you need secondary air. And overall, there's about 15 foot of air that are used as primary and secondary air for every cubic foot of gas that is burned. So typically, it's 10 cubic foot of air goes into the burner. Theoretically, that's all the air the burner needs for complete combustion. And then we have 5 cubic feet of air that's introduced around the heat exchanger, and that's our secondary air. And that's 50% more air than we need. And that's why a lot of times we call that 50% excess air. Now, depending on how carefully we control the draft on an appliance, we can get that excess air down. And if we get it down to 0%, theoretically, that would be stoichiometric combustion or perfect combustion. But we don't do that because we always want to give a furnace excess air for safety reasons, because we want to make sure that all the carbon is converted over to carbon dioxide. So we always supply the burner with some excess air because we don't get perfect mixing of the gas and fuel as it goes through the combustion process. So the excess air is provided to make sure that it's consumed. Now, because this draft hood is there all the time, guess what the draft hood is always doing?
It's always inserting additional air into the flue.
Into the flue, right. And where's that air come from? Typically, when you're talking about a draft hood, where's it get its air from?
Inside the space around the furnace.
Yeah, inside the furnace, around the basement. Typically in northern climates, we're in a conditioned space is where the furnace is at, in a basement. In other climates where it's outside, it's not as big of a deal. But let's think about what happens there for just a minute, because now a gas furnace requires an additional 15 cubic feet of air per cubic foot of gas burned to go up that draft hood every hour. So if we're talking 100,000 BTU furnace, right, 100,000 BTUs per hour, if you took about 1,000 BTUs in a cubic foot of gas, you're talking about 100 cubic foot of gas, right? And if we multiply that times 15, that's about 1,500 cubic feet per hour of air required. So that air is constantly going up the stack 24 hours, 7 days a week. And what temperature is that air typically, you think, in a conditioned space?
Temperature of the air in a conditioned space in the winter, let's say 68 degrees.
68, 70 degrees. Obviously, if we kept exhausting air all the time, what would happen eventually in our house?
Get under negative pressure.
It gets under negative pressure. Now, again, older homes, we had leaky windows, leaky doors, door seals. It wasn't a big deal. We just pulled in fresh air to burn all the time for that draft hood equipped appliance. It just pulled in that fresh air and it got all the air it needed. But if we're heating air from 0 degrees outside up to 70 degrees, right, because we're bringing it in the house, we got to heat it up, and then we're turning around and exhausting it again, well, it's just like having an open window in your house and you're just constantly exhausting the air you just heated out your home. And so the draft hood became a big source of energy loss in a home. But it did, I think, important things. One of them was to provide us with fresh air in the home, because as the draft hood exhausted air out, then we had a continual supply of fresh air coming in, and the home would breathe a little bit and you get some natural ventilation in the house. The problem with that is that natural ventilation creates drafts, so they're uncomfortable. And also, if you go back to our psychometrics, if we were to take 0 degree air at 100% relative humidity and then heat it up to 70 degrees, what would the humidity do?
And the humidity would drop.
Yeah, it might drop to 10, 12%, maybe 15%. I don't have a psychometric chart in front of me.
That's why it took me a second there. I was like, does he actually want me to calculate this?
No. I just wanted you to understand the relationship. Humidity is going to go down a ton, right? If you just visualize the psychometric chart in your head and you just go at the bottom, it's really skinny and you just went straight across, you go, oh, wow, that'd be down in the 30% region, maybe lower. And that's as dry as the Sahara Desert is in the summertime. So now we're bringing in all this air because, again, when the furnace is running, we're using 30 cubic feet of air. When the furnace is in standby, we're using 15 cubic feet of air, right? That 15 cubic feet is constantly being exhausted up the diverter. So the trick was, first of all, we always wanted to carefully control the amount of draft. So on some appliances, you'll see a draft, not only a draft hood, but also a draft control. And the draft controls are typically, you see like Field, a company named Field makes them, Field draft controls. And a draft control is just a way, if you had a really, really tall chimney, to additionally control the draft, because the whole purpose of that draft hood is to separate the appliance from the draft so that the natural flow of gases through the heat exchanger is what induces the secondary air flow into the burner. And if we're to block off that draft hood and let the chimney suck on that, and then it would pull all the heat up through the heat exchanger, and it would cause stack losses, elevated stack temperatures, and other issues. So the older furnaces, that's one of the standby losses that we wanted to eliminate. So what I'm trying to walk you through here is a little bit on history of furnaces. Understand that we are not burning gas any more efficiently than we did in 1930. In fact, in 1930, we knew everything we needed to know and probably knew more about burning gas than most guys know today. What we did on modern furnaces was two things. One was we eliminated standby losses, and two, we better controlled the ignition so we didn't have things like pilot lights and things like that. And then three, we figured out that with the correct materials, we could actually make furnaces that got the latent heat or the moisture out of the flue gases, and we got additional latent heat for combustion. We hit the old gravity furnace, didn't have a blower. Later, they retrofitted blowers on those to give it forced convection, which helped to move the heat more efficiently through the house than gravity. And also, it provided a means to filter the air, because the old furnaces didn't have filters. The air flowed through, just was cold air in, hot air out, no filtering mechanism in there because the drafts were so small going through a furnace that we couldn't filter the air. We didn't have any kind of filtering medium. They added blower in. Then after they added the blower in there, they decided, well, the next thing to do is to eliminate the pilot. And they went to things like spark ignition or glow wire ignition, where we actually used a piece of, I think it was nichrome wire, and they just drew a small current through it to light the pilot, and they let the pilot on demand. And you'll see all these, if you work on enough gas furnaces, older stuff, you'll see all these different controls and changes along the way. And it's just really cool to see it. So now we get into the 1970s, maybe early 80s, and we had the gas crisis. We really didn't have a crisis. It was all lies, I think, at the time, because we still have gas today. Whatever it was, all of a sudden we became very aware of the amount of gas we're using, and we decided that we need to make homes use less fuel. And back in that day, if I'd have to look at the exact dates, but I mean, they actually had public campaigns on there to turn your thermostat down to 60. You need to keep your home cool, and people just weren't into that. They wanted comfort.
That was Jimmy Carter's famous speech. Be a patriot, put on a sweater. I remember that.
Yeah, I always thought it was, I'm Jimmy Carter and I like peanuts. But I guess.
All right, Jimmy, if you're listening to this, we love you, buddy. I mean, Jimmy's still around, so be nice.
Yeah, he's a good guy. But he was a tree hugger at heart.
True.
We had all these new modern efficiency furnaces. Well, let's think about what we did here, because now we introduced, what do we want to do? How are we going to make furnaces more efficient? Well, again, it's about eliminating the standby losses. So the first thing we noticed is, in fact, if you go back to the older 70s, these were like the 60% furnaces didn't have a blower. Then we added the blower. We got the efficiency up around 70%, 72% efficient. Then we jumped from 70 to 80% efficient. And there's a couple little things that went in between there. One was bimetal flue dampers on these old 70 pluses. So we used to have a bimetal flue damper that sensed the heat in the flue, and it would open or close to allow the furnace to draft. And believe it or not, your furnace would spill in the basement for 3 to 5 minutes while that bimetal warmed up before it would open far enough up to start to draft properly. And that was totally acceptable. And what they did later on was they added in a spill switch that connected to the draft diverter. And if the spill switch would not trip until it hit, I want to say it hit 200 degrees or 150 degrees Fahrenheit. And so that took a little while for that spill switch to get that hot. So your furnace would spill and spill and spill. And as long as the bimetal opened up before the spill switch tripped, then everything was considered okay. And your furnace would start to draft naturally. But a little bit of carbon dioxide, water vapor, and heat entered your basement, not carbon monoxide. Carbon monoxide is a product of incomplete combustion. We had these furnaces that they did that. And then we also had retrofit kits. Guys remember probably the G60, Johnson Controls G60, that you could go in there and you could convert a furnace over to spark ignition. Those were the first flame rectification systems, at least that I remember. And they had the G60 and they had the flue damper, and they had a lot of furnaces that were using this mix for a while. And then in the 80s, we came out with a draft-induced furnace. So let's think about what happened there for just a minute, because now we got this furnace that went from 60% efficient to 80% efficient. Now, again, this is not combustion efficiency. This is appliance efficiency. You've got to look at standby losses, because we're not burning the gas any better. And in fact, I think in a lot of cases, we ended up burning it worse because of the new burner designs. So we get into this more complex heat exchanger designs because they're making furnaces more compact, and they're now draft induced, and they're actually made out of sheet metal now for the first time. And the furnace, the flame, went from a carbon luminous flame to a blue flame. So now we've changed the method of heat transfer of radiation in carbon luminous to convection, and we're now heating up the hot gases of flue gas, right, as they go through the furnace. And we had actually, going back to some of those 70s, obviously, we're skipping ahead a little bit here because some of the 70s also, they were still draft hood equipped and used steel heat exchangers and used convection to heat with, but sort of skipped over those a little bit. But those were in there also. There's a long furnace history here. But we get into the 80%ers, and we've eliminated the standing pilot. We've eliminated the draft diverter. And we've eliminated the standby losses of draft, and we've got this 80% efficient furnace. So the draft inducer motor on a furnace is designed to replace the draft hood. And the draft hood obviously was designed to disconnect the furnace from the draft, right? But now we got this really complex heat exchanger design. And the heat exchangers, they're going left and right and up and down, and they have all kinds of narrowing passages in them, and all kinds of things are changing in a heat exchanger.
And it's just because now we can, right? I mean, that's the reason why they've made all these changes, is because when you have forced draft, you can do that.
Not because they had forced draft, it's because if you're going to change the method of heat transfer, if you're going to go from radiation to convection, you're going to have enough surface area and enough time, because heat transfer is a function of time, temperature difference, and turbulence. You got to have enough time, temperature difference, and turbulence to extract the heat out of that gas. So the more surface area that we could expose, the more heat transfer by convection we were going to get. And it wasn't because we could, it's because they had to, because they wanted to get all the usable heat out of the flame. Typically, we'll want to see a stack temperature of somewhere of 325 degrees to 500 degrees on the outlet. And if it's much above 500, we're wasting energy. If it gets down below 325, then we're going to have a chance of condensing in the flue, because we also need enough heat energy to make it all the way from the furnace all the way out to the top of the chimney without condensing in the flue. And with our old 70%ers, well, guess what they were doing? They're constantly drafting. And by the constantly drafting, even if it did condense in the flue, it was going to dry that out with fresh, dry air from your house, constantly pulling air through the chimney, and would keep the chimney from corroding and falling apart. The liners in the chimney were tile liners, and everything got nice and hot and stayed hot. As long as the chimney stayed hot, the chimney stayed in really good condition. So when we got into these 80%ers and we all of a sudden slapped the draft inducer motor on there, now the function of that draft inducer motor was to assist in pulling air through the heat exchanger. Because the heat exchanger, just if you lit a fire in that heat exchanger, it would not naturally, there was too much restriction for the natural draft to pull through that heat exchanger. It's just way too restrictive. So the draft inducer motor now was designed to create a pressure at the heat exchanger outlet that was equivalent to that of a natural draft appliance. And because we could engineer the draft now on that draft inducer, we could actually carefully control the amount of excess air that we introduced into the burner. And now we got a furnace that we're not introducing any excess air into the system except for through the heat exchanger inlet. We no longer have a draft hood where we are constantly supplying some fresh air up for the chimney. So not only do we have to introduce enough air for combustion, but we also had excess air for dilution. So remember, I told you that the old furnaces, they might have 20% excess air above the heat exchanger. The new ones, all the new 80%ers, we want to have at least 50% excess air. All right, and the reason we require 50% excess air is not only for safe combustion, but also to provide some air for dilution. And if we don't provide air for dilution, what's going to happen is the flue gases are going to condense in the chimney. And if they condense in the chimney, we're going to have a whole host of other issues in there. Very important to understand that. Now we have a couple of different things going on, because if the draft inducer motor doesn't start and we have a call for heat and the gas starts firing in and there's no air coming in, where are the flames going to try and go?
They jump back out at your face. They roll out.
Jump back out at your face. We're going to have a rollout out there. That's not a good thing. So we needed a rollout switch in there. And how do we prove the draft inducer motor was actually running?
In modern systems, we use a pressure switch to do that.
And that's the same way we did it in the old systems. The pressure switch is used to create or sense the draft that's created by the draft inducer motor. So the first thing that happens, the inducer motor starts, creates a draft, closes a pressure switch. That tells the furnace the ignition cycle can continue, right? Now, the other thing that we did with these new modern furnaces, because again, we had no draft on there, was we eliminated the pilot light. And again, you will find furnaces out there that are 80%ers that have a pilot light, believe it or not. Because even though the draft inducer motor shuts off, there's still a little bit of draft through the fan wheel. That's enough to exhaust out the pilot gas in there. We could go on for hours on how many furnaces that were actually designed and all the in-between stuff that happened. It was a progression through our industry. And also it's driven by marketing. Guys are like, oh, I hate hot surface igniters. And Rheem would go, oh, we're coming out with a furnace with a pilot light. And guys are like, oh, I understand pilots. I'm going back and I'm selling all these furnaces with pilots. And that's what guys would do. Then I hate spark ignition because I don't understand it. Well, we have a new hot surface igniter. It just glows like a light bulb. You understand a light bulb? Yeah, I understand a light bulb. Okay. Well, we've eliminated the spark, which is so confusing, and we're going to go to a light bulb to ignite your gas, right? So a lot of these are also their marketing decisions along the way also. And that's just the way our industry is. Nobody likes change in the industry. We get this 80% efficient furnace, and obviously it's got a blower, just like the 60s and 70s that as they grew up through there. We eliminated the draft hood, eliminated the pilot. We got now a hot surface ignition. And furnaces, we consider them all 80%ers. Now, the question I always ask people is, why don't we see 82%, 83%, 85%, 87%, 88% efficient furnace? Why is it that we go from 80 to 90%? Any idea on that, Brian?
I think I know the answer to this one, actually, because as soon as you go above 80%, now you're bumping into the point where the exhaust is going to start condensing moisture. And as soon as that starts happening, well, you might as well go up and extract all the heat, all the latent energy out of it, as opposed to only doing it partially.
Yeah, you're 100% correct again.
The point is that the reason why is because if you're going to get into the condensing range of combustion, then you might as well take it all the way and get all the latent heat out that you can, because otherwise you have to build a furnace differently if you're going to be condensing the combustion byproducts.
That's sort of right. I would actually say it's because if we get the stack temperature any lower, we're going to condense. And if we condense in a non-condensing appliance, it's going to lead to a host of huge problems. Induced draft motors rotting out, heat exchangers rotting out, furnace chimneys falling apart, leaching white stuff on the outside of the chimney as it eats out the mortar, all kinds of things that literally destroy a non-condensing appliance, because that non-condensing appliance doesn't have a heat exchanger that's designed to be corrosive resistant. In other words, it's not made out of stainless steel. And so it is going to literally fall apart. And when you see 80% efficient furnaces that are full of rust, that have all these other issues, there's two things you need to look for. One is obviously chemicals. And again, we'll talk about that in a later podcast. Chlorine, bleach, dryer sheets, things like that. Bad around furnaces. You don't want to have those around furnaces. But the other thing is you have a condensing taking place because the furnace is not set up properly, or it doesn't have enough draft, or for whatever reason there's something else going on there you got to look at. These 80% furnaces, obviously they have a primary heat exchanger. They have no secondary heat exchanger. They have a lot of times serpentine designs. And as the designs get more and more complex, the heat exchangers get smaller and smaller and smaller. Hence today the furnaces are 3 foot tall, right? Because they have very complex heat exchanger designs that allow them to extract all the heat out of the flue gas in a very small amount of area. And basically 3D modeling, CAD, all those kind of things allowed us to make these more complex heat exchanger designs, where they used to have a clamshell, which was just two pieces of metal that were stamped and then welded or riveted together. But all those heat exchangers on those older 80s, that's just the way that they were engineered. They're non-condensing appliances. And now the appliance, because it gets its excess air for combustion through the burner and through the secondary, the input on those things becomes critically important. Another thing I want to talk about in a later podcast, but is commissioning a gas furnace, because there's only a couple things that we can do, and if we don't do them right, it's going to cause just all kinds of nightmares with furnace operation. So then the next thing that happened was we got to the 80, and 80% of furnaces were only around for a short time before they actually came up with a 90%. I think probably the first real 90% I remember was a Lennox Pulse. I'm sure there was other ones out there, but Lennox decided that everybody wanted a moped in their basement, and they came out with a Pulse furnace, and it was probably one of the best 90-plus furnaces ever manufactured because of the way it worked. Pulse combustion is extremely efficient. It was basically an explosion, and every time it exploded in the heat exchanger, it would create a vacuum that would pull in the next mixture of gas and air, and it would explode again, and next mixture of gas and air explode again. And after it lit, the previous explosion lit the next one. So there's still some gas, sort of like glow plugs in your diesel, right? Once your diesel engine's running, you don't need to run the glow plugs anymore. It'll just keep running with, from the hot flue gases lighting the next charge coming in. But the 90 plus, if we eliminate the Pulse furnace for a minute and we go back to condensing furnaces, really the only difference between an 80 plus and a 90 plus, the big differences are we've added in a secondary heat exchanger. And the function of the secondary heat exchanger is to pull additional heat out of the flue gas and basically condense the latent energy out of the flue gas, but it pulls the heat and the humidity out of the flue gas to get this additional efficiency. Now, a couple of interesting things here. you'll see that we go from like 90, 91, 92, 93, 94, 95, 96, 97%. I don't know if I've seen any above 97% combustion efficiency or 97% efficiency, but I think 97% is about where they top out at. And when we look at these furnaces, you're going, well, how do we get from 90 to 97%? Well, we actually did it by not just lowering the flue gas temperature, but also extracting the latent heat of combustion, the latent heat energy out of the flue gas, which is the moisture. Just like when you start your car and it's running, you see moisture dripping out of your tailpipe. Well, where's that moisture come from? Well, it's a byproduct of combustion. It's anytime that we're burning fuel, a byproduct of the fuel is water. And that water, if we turn the water vapor into liquid water, we get about 970 BTUs a pound of energy out of that that's condensed. So the original 90-plus furnaces, realistically, all they did was cool the flue gases down. And in fact, there was very little condensing that took place, if any. If you go to an old 90-plus furnace and you actually pull the condensate drain off and you watch it run, you might get a drip or two of condensate out of it as it's running. And it was still called a condensing furnace because it ran at the threshold of condensing. But they really didn't condense much of the heat energy out. Now you get into a 97% efficient furnace, and it'll run an 1/8 to a 1/4 inch stream out of that same trap because now we're extracting additional heat energy out of the flue gas and we're getting into condensing range. We're deeper into the condensing range. We're getting the flue gases cooler, but the other thing that we're more carefully doing is controlling the excess air. Remember we said excess air is necessary for safe combustion, but excess air is also what kind of air? What was it used for in the 80 plus? It was dilution.
That's right. Dilution air. Okay, that's the word.
We brought our dilution air in along with the combustion air. So now the dilution air is going all the way through the heat exchanger on the 80. In a 90% efficient furnace, what happens if we add in dry air into the combustion process and we add additional dilution air in? What do you think is going to happen to our condensing on our condensing furnace?
It's not going to condense because you're adding in dry air.
Not going to condense. We're drying the flue gases out, right? So this becomes like super important if you're going to get this 97% efficiency out of this furnace that you have the input correct. Again, when we get into some more detail on setting up furnaces, I'll go through this, but it is absolutely critical that you have the excess air trimmed to the correct amount and you have the input correct on that furnace, because if you don't have it set up properly, the dilution air is going to dilute the flue gases and you're not going to condense. You're not going to get that efficiency out of your furnace. So, it's got to be 10 years ago now. I actually went to CSA Labs, which is the old AGA laboratories in Cleveland, Ohio. The first thing they do when they test a furnace is they take it out of the box and they pull the orifices out of it and they put new orifices in it. Then they clock the meter and they make sure the input's 100% correct. So not a single furnace is ever tested as it was delivered from the manufacturer, because CSA doesn't really care what orifices come in it. What they care is what is it rated. So they look at it's 100,000 BTU input. I'm going to put 100,000 BTUs of gas to it, right? They have a calorimeter there that measures the exact amount of heat energy that's produced by the gas. They know exactly what size orifice they need. They get the input spot on to the furnace. Then they test it as it's published to make sure it meets its safety and efficiency requirements. And doing it the way CSA Labs does it, every single time the furnace will produce the same results as it was tested at the laboratory it was manufactured at Carrier, Trane, Lennox, whoever. But because a lot of times in the field don't go through and set up the furnace properly, it never realizes its efficiency. That's one thing that we'll cover in another podcast. But I think it's just very interesting when you understand, when you start looking at how this industry works and how the efficiency works. Just because you pull it out of the box and it says it's 97% AFUE on the label doesn't mean it's 90% AFUE as you set it up. And so just important to understand. So now we've added in the secondary heat exchanger. We dropped the stack temperature down to below 120 degrees. The only thing coming out of the flue gas now is carbon dioxide, water vapor, and heat energy. And we got that heat energy down to a minimum. We're condensing as much of the moisture in the secondary heat exchanger as we can. We can't condense 100% of it. We have some of the exhaust gas coming out the side of our house as a little cloud, just like it's a dryer vent. And we've now changed the draft inducer motor from a metal one to a plastic one because A, lower temperatures, but B, corrosion resistance. Because flue gases also contain acids, primarily because of chemicals in your home. If you have a sealed combustion where it's pulling air from outside, which I would highly recommend you never, ever install a condensing furnace without the inlet pipe on, because it'll tear up that furnace. It'll cut years and years and years off of it.
Not only that, but you're losing half of the benefit. I mean, another benefit is that you don't have the actual losses in the home from having to provide combustion air and putting your house in a negative pressure conditions, besides it not tearing up the furnace.
Right. Oh, it's a huge, but the chemicals, the chlorine, the formaldehydes, aldehydes, things in the air that burn that cause other problems with the flame is huge, right? So we don't want to have that happen. Now we've got plastic venting. We're venting with PVC pipe, again, because we've got flue gases that are condensing. We've got to handle that condensate. Draining that condensate back to the furnace is going down the drain. We're getting all the heat energy out of the flue gas now that we possibly can. And we've eliminated, again, the pilot. We've eliminated the draft diverter. We've eliminated draft, essentially, because we're not connected to a chimney anymore. So all the draft we're creating with a draft inducer motor. We got a secondary heat exchanger, and inside of there are what are called turbulators. And turbulators are just simply a twisted piece of stainless steel that is designed to basically scrub the flue gases against the walls of the heat exchanger. So if you ever pulled out the center of a hot water tank or anything, it's got like this spiral staircase going up inside, and it's all to increase the amount of time that the flue gases are in contact with the walls so that it maximizes the heat transfer. So we got this primary heat exchanger that's got a very complex design that's getting about 80% of the heat energy out. And then you take that 80 plus furnace and you just basically duct it down to a secondary heat exchanger. And that secondary heat exchanger pulls out the additional 10% of the energy out of the flue gas, or up to anywhere from 10 to 17%, depending on the appliance. And then we get a little bit of water going down the drain, and the thing runs like clockwork now because we got all these things that we've eliminated. Now, obviously, we got a couple other things we've done with furnaces and two-stage appliance. So let's just talk about that for a minute, because I've got a two-stage in my house. Are two-stage appliances, Brian, you think more or less efficient than single-stage appliances?
It's an interesting thing because I don't see how they could be more efficient. To me, in my little southern Florida mindset, it sounds like having two-stage electric heat strips or something. And it doesn't. You've got the combustion efficiency. Why would bringing in a lower fire stage be of any benefit?
Well, why do you bring in a lower strip heat? Why do you modulate strip heat?
You do it because you're wanting to maximize the use of the heat pump as your primary form of heating. And so you don't want to bring on more strip heat than you need because it's an inefficient form of energy.
Right. And I also use strip heat to temper the air sometimes, right, to provide additional comfort, right?
Right.
Whenever we're talking about heating or cooling a home, ideally, we want to have heat coming out of the registers all the time. In fact, I've got a Rheem Contour in my house. It's a full modulation 90 plus. I think it goes down to 30% up to 100% or 35%. I can't remember. The whole concept behind that furnace is once the weather here drops below 40 degrees, my furnace runs continuously. It never shuts off. If it never goes above 40, my furnace will run 24 hours, 7 days a week. And you're thinking, how the hell can that be efficient, right? Well, what we're doing is by multi-stage or modulation of appliance in a house, what we're doing is we're replacing the heat at the same rate that it's escaping out of the house. And a two-stage appliance or a modulating appliance, what it's going to do is it's just going to run at a lower input, which means that, let's say if we cut the input in half, it's going to have to run twice as long to satisfy the heat loss of the house. Right now, heating a home is a dynamic thing, so we're losing heat at a very specific rate because it's hotter inside and colder outside. Once the furnace's job is to actually replace the heat at the same rate that it's going out through convection, conduction, radiation of the building materials. So when we're looking at running this furnace in our home, the perfect furnace is like the Rheem Contour or something similar where we're going to replace that heat energy at exactly the same rate we're losing it at, because now I got heat coming out of my registers all the time. And I've significantly increased my comfort, but I've done it at the expense of a little bit of efficiency, because my furnace does not run 97% efficient when it's in low fire. It probably runs around 92% efficient in low fire. So most of the time, my modulating furnace is losing a little bit of efficiency, but I'm doing that at the sacrifice of comfort. That's not a bad thing. It's just a reality of two-stage appliances, as you're going to find out that because the heat exchanger is a fixed design, because the draft inducer motor only has 2 speeds, and here's the other thing we don't think about all the time with a draft inducer motor, but we actually size the draft inducer motor it's got a inlet and exhaust. And when we design that thing, we're always looking at what's the maximum flue length. So if your maximum flue length is 100 foot of flue and we have it connected to 5 foot of flue, well, it's going to obviously have a lot less restriction on it, and it's going to move a lot more air through the heat exchanger than it should, or than it could. It's just because we have the short venting system on this thing. Same thing with a 90 plus. All that comes down, and we really don't have any way in the field of tuning the vent system, nor should we ever tune a vent system. That's really the wrong way of doing it. And obviously, we don't want to put 5,000 elbows on it to give it an equivalent length to the longest length, because it's just not going to net you that much efficiency. We're talking about a couple percent efficiency on the furnace. You might be losing because the vent system is not optimized for the installation, right? But that's just a function of when we provide flexibility for multiple kinds of installations, we also sacrifice a little bit of efficiency. It's just one of those things out there that we got to deal with.
Did you just reveal the new upcoming technology of the variable speed inducer that also is constant torque like a ECM motor is, where it actually senses the back EMF and adjusts output based on the length of flue? Do you think that's a technology? I mean, does that exist, or is that something that may occur?
I think York has actually got a furnace that does that. It measures the box pressure, measures the pressure inside the furnace, and adjusts the ECM motor. We are seeing some with ECMs. I have at home a Harman wood stove. It's a pellet stove, and it's actually got a potentiometer on the combustion blower. It's actually a wood stove that's got a combustion blower on there. And you can actually tweak the maximum speed of the induced draft motor based upon your excess air requirements. So I could actually dial in my wood stove so I have optimal efficiency for my wood burner, actually probably better than I could do my 80 plus furnace. The thing is when you're installing a furnace, there's things that we could do and things that we should do and things that we should not do. And trying to tweak additional efficiency out of a furnace by modifying the design is a big no-no, because you're violating its listing. It's listed to be installed and operated in a certain fashion. And if you modify that, you may be taking on some liability as the manufacturer of that furnace, that because you're changing the way it's designed, right? And some guys in the industry will tell you, oh, you can do whatever you want. Once you buy the furnace, it's yours. But go to court and see how that works for you if you got a factory rep from Lennox telling you that you modified his furnace after he designed it, you modified it, you're not operating it the way that's intended, and see how it works for you, right? I've seen that kind of stuff happen before, and I didn't mean to point out Lennox here necessarily. They just popped into my head, but I've seen that kind of stuff happen before, and I'll just tell you right now, you're not going to win. Everybody's going to go back to the installation manuals, and they're going to look at all those things and see if it's put in the way that it was listed and installed. They'll pick apart the installation to make sure it's installed correctly. But we'll cover some of this in the next segment up there. Hopefully you got a little bit about an idea of some of the differences between the furnaces. Hopefully some people down there in Florida that have never seen a furnace before, this will be an interesting podcast for them. But I think gas burning is way, way more complex and interesting than a lot of guys actually understand. So
give it credit for. I think it's fascinating. So let's just do a quick summary of the things that we've covered and sort of the history. So initially we start off, problem with furnaces is that they catch stuff on fire. So we make some tweaks to catching stuff on fire, and then we start to realize, okay, this carbon monoxide thing is now an issue. We need to pay close attention to that. We do some things with that and some additional tweaks to safety. We start looking at different types of safety controls, and we say, okay, well, now we've got some excess losses.
One more thing we didn't talk about, I think is just cool, because again, going back to the 60s, Jimmy Carter had us do another thing, which we started weatherizing homes. So we had all these homes that had draft hood equipped furnaces, right? And all of a sudden now we're caulking everything shut. We're sealing windows shut. We're sealing doors shut. We're putting a weather stripping, all kinds of guards. So now the house can no longer breathe. And basically, if you want to understand how the house works as a system, just put your hand over your mouth, right? Because that's effectively what we did to these draft hood equipped appliances. We put our hand over our mouth, and now the furnace can no longer get air to burn. So if it ran too long, now, again, we're causing carbon monoxide problems because now we're not providing enough air for complete combustion. So sorry to derail you, but I just thought that was interesting.
It's a good point, because we didn't have as many carbon monoxide concerns until we started making buildings tighter and until we went away from natural draft appliances with draft hoods, because that old design made it less likely that carbon monoxide was going to be an issue. And so then as we started going away from that type of appliance, now we had more, and we went to tighter buildings, we had more and more problems with carbon monoxide. So, of course, that's a huge issue, something we take seriously. So we still take seriously things not catching on fire. We have all these safeties. We have all these designs that help deal with that. And then we went into an era where we started taking carbon monoxide very seriously. And then we went into an era where we started taking efficiency very seriously, the actual fuel consumed. And that's when we started going into 80% furnaces with these more exotic heat exchanger designs, and then later into condensing gas furnaces where we not only extracted heat up to the 80% range, but we went above that. And now we had to start dealing with the condensation of the combustion products. And so then from there, now we're talking about the products, modern products that are even more comfortable because they maintain set point. I mean, that's what it really comes down to. When you have a modulating or a high-low fire, multi-stage appliance, it helps maintain that set point more steadily. And so you're not bouncing up and down as much, which does relate to human comfort. But like you mentioned, that is actually at the expense of a little bit of efficiency in a lot of cases.
Now, here's the cool thing that we've just done. I want to show you how this all came full circle. Because the old-fashioned furnaces, they're cast iron. You had this huge hunk of cast iron. You heated it up. Took forever to heat up. But that thing would cycle the burner off and on. Once the cast iron got hot, all it would do is continually emit heat, right? You always had warm air coming out of your register. And then we got into the newer furnaces. They're all made out of sheet metal, and they would blast heat out and then shut off and blow cold air or no air. And then blast heat out and cold air, blast heat out and cold air. So now what we've done is we've taken this completely full circle, and now we've made that furnace with full modulation back into almost a gravity furnace. We've got very low airflows. We've got a modulating input. We've got heat continually coming out of the register. And so we're reintroducing comfort back into the appliance and efficiency at the same time. Back in the day, it was all about comfort and all about comfort. That's why we heated a home. People wanted to be comfortable. And as we got more and more efficient, we got less and less comfort. And it got to the point where people didn't even know what comfort was. And today, now that we're trying to sell comfort to a whole generation of people that have never experienced it, it's become a challenge on our industry. But that's the kind of heat energy that we want to have. That's like when we talk about radiant heat, and it's so comfortable. Radiant heat, once it gets the objects warm, they radiate heat and they stay warm. Radiators, steam heat was absolutely incredible because that big chunk of cast iron got hot in your house and continually radiated heat to your body, and you felt comfortable in the space. So these older systems, we're trying to get some of those characteristics back that we used to have and do it in a way that we're getting the maximum amount of energy out of the flue gases today.
Well, if you even think about, you mentioned a really interesting thing, because people will talk about how they feel. There's something special about sitting around a fire, right, and feeling that radiant heat. The only problem with the fire is sometimes it gets a little too hot, so you got to shield your face or whatever. But radiant heat is a very natural way that we feel comfort. On a cold day when you're outside and the sun's beating on your back, it really feels great. That's how the human body was designed to be warmed. And as we've gone more and more to forced air convection, where we have temperatures that are jumping all over the place and it's all through convection and conduction, we don't naturally feel comfortable in those environments.
Right. Yeah, it's 100% correct. And that's what we're trying to get back to, is that feeling of comfort with forced air, which happens to be about the worst way you could heat anything. But it's because of the advent of air conditioning, and we wanted to do one system to heat, cool, humidify, dehumidify, and filter our air, that we're giving up one thing for another. And now you see people building homes where they're using a mini split for cooling and they're using radiant floor heating for the heating, so they can get sort of the best of both worlds. We're going back in and we're saying, why are we trying to do everything with one system? And even like whole house dehumidifiers versus trying to use your air conditioner as your dehumidification system, right? It's not necessarily the most efficient way of doing it. So now we introduced the whole house dehumidifier or the whole house humidifier, or we're doing things differently because we're tired of sacrificing comfort. But one other interesting thing, just as to close this thing up, is we talked about violating a furnace's listing. And I don't think most people realize this, but our industry, the HVAC industry, the heating industry, whenever you see that sticker on there that says UL, that's an underwriter's listing, right? And underwriters typically work for who? Who do you hear associated with underwriters?
Underwriters work for insurance companies.
Insurance companies, yes, because our entire industry, the HVAC industry, was driven by UL testing and underwriters' laboratories. And what happened is people would die from fire. Then they would say, oh, we don't want to pay a claim again on that, so redesign the thing so it doesn't put out fire. People would die from carbon monoxide. Ooh, don't want that to happen again. Let's redesign it so it's safer combustion and provide excess air. People die from this or that. Everything we do is, even your International Fuel and Gas Code, your furnace designs, your electrical codes, everything that we do, the reason all these codes and all these standards were invented is because when people died and insurance companies had to pay out money, they wanted to have ways of mitigating risk. So by controlling the furnaces and by saying, okay, to have a UL listed furnace that has to meet these qualities, that means if it's installed in the way that it's listed, in other words, the way that it's engineered, that it's going to be really, really safe and most of the risk has been mitigated. Where we have mistakes in our industry, and this will be, I think, our next podcast, is when you don't set that furnace up properly and it's not installed according with this listing and something happens. Typically, that's the only thing that will cause something to happen. That's when we have problem. It's just interesting when you look at the history of the AGA and CSA and all the things that have happened, how much of it is really comes back to not only comfort, but a huge, huge part of it, safety. Probably more than anything is we don't want unsafe appliances in our homes. So it's just, there's a lot of history, a lot of interesting stuff with gas, that's for sure.
Yep, the core motivation that humans have of not wanting to spend money they don't need to spend and also not wanting to die. That's a good driving motivation for the industry, I guess.
Yeah, I think so. I think I'll try and avoid those things for the next podcast.
Until the next podcast.
Until the next one, yeah.
All right, Jim.
All right.
Thanks for spending the time with us.
Thanks, Brian.
All right. A big thanks to Jim for everything that he does and for coming on the podcast. He has committed to continue coming on the podcast. We had a little hiatus there. We've both been very busy. He's got all kinds of irons in the fire right now. Obviously, the MeasureQuick app, which you can find by going to measurequick.com, is a great application. They're doing a lot with that, and so I would encourage you to go check that out. Obviously, Jim also owns Redfish Instruments. They've got some interesting things going on. You can go check those out. But we got some new things that are going to be coming up with us and Jim in the future that you're going to be very interested in, so stay tuned to that. As always, if you want more good HVAC and trades content in podcasts, if you're a podcast addict like me, well, actually, you could use the Podcast Addict app in order to listen to these podcasts, but you can go to bluecollarroots.com, bluecollarroots.com to find all the other podcasts that are part of the Blue Collar Roots Network, and you can go to hvacrschool.com to find everything at HVACR School, which includes a near daily tech tip. We call it the Daily Tech Tip. It isn't necessarily every single day, but we try to get 4 to 5 out a week. Good short tech tips that will hopefully help you with your technician life. All right, so if you're anything like me, you used to have to work with line covers that were made of metal. And I'm not the best with sheet metal, okay? I'm in Florida. I've never done a lot of sheet metal work, and I could never get a metal line cover to look decent. And then when you had to paint it, getting the paint to stick was always a challenge because, it's metal. But then out came these different line cover products. And one of the products that I really like is the RectorSeal Slim Duct product. I think it's probably the best looking line cover on the market. And it comes in different sizes and has all the fittings. But also RectorSeal makes another product called Fortress, which is a line cover product. It actually comes in a kit, and so it has smaller sections. I think they're 4-foot sections. They come in a box and different fittings, and it's a really nice value option if you need to do a line cover job. If you have a quick line cover job you need to do, you can actually keep one of those kits on your service van, which is really nice. So for all of your line cover needs, you can trust RectorSeal with both the Slim Duct and the Fortress products. I don't know if you heard this. I probably shouldn't even tell you this, but oxygen and magnesium, they're dating. I was like, OMG. All right, thanks for listening. We'll talk to you next time on HVAC School.
Thanks for listening to the HVAC School podcast. You can find more great HVACR education material and subscribe to our short daily tech tips by going to hvacrschool.com. If you enjoy the podcast, would you mind hopping on iTunes or the podcast app and leave us a review? We would really appreciate it. See you next week on the HVAC School Podcast.